So we've been looking on Monday. We looked at Thevenin's theorem. In case you forgot it already, this is one of the really important. I have students who I run into them from time to time. They become computer engineers or like oh yeah, Thevenin equivalence really important in what you do after you transfer. So if you're a mechanical engineer, probably not so much, but it is a really powerful theorem that allows us to simplify circuits a lot. So any combination of voltage sources, current sources, and resistors can be replaced by a single voltage source in series with a resistor. And we find the Thevenin voltage as the open circuit voltage of the terminals. And the Thevenin resistance is the equivalent resistance at the terminals of interest, right? And these are the terminals A, B that we're looking at. And our Thevenin is the equivalent resistance at those terminals with all the independent sources turned off. Those terminals are completely arbitrary. You have to be told, at what two terminals to do the Thevenin equivalent at. If you choose a different point in the circuit to do that, you'll get a different equivalent circuit. It's really dependent on where you're looking at it. And we find our Thevenin the easy way. When there's just independent sources, we just turn off the independent sources and find the resistance between those two terminals with the independent sources turned off, where the voltage sources become short circuits and the current sources become open circuits. So we did example 5, kind of played around with that, and Matthew actually played around with the potentiometer in the lab yesterday. That's one of those things. So that's what this symbol is. This is a variable resistor. A resistor with an arrow through it means you can change the value. And he used it to change the sensitivity of the dusk to dawn sensor for the application of diodes and transistors. So when he turns it one way, it wants to illuminate real readily, and another way, it doesn't want to light up at all, unless you're shining a light straight at it, or whatever, the other way around. With dependent sources, it's a little more tricky. You cannot just turn off a dependent source because they respond to what's going on elsewhere in the circuit. So you still define the Thevenin voltage as the open circuit voltage of the terminals, but you have to find our Thevenin by connecting a source to the terminals A, B, and that test source could either be a voltage source or a current source. Typically, we just let it equal to 1, and then we solve for the VOC, or we solve for the we solve for the VO at the terminals, whether it's a voltage source or current source, and the I. Once we get the V and the I of this test source, which is at 1 amp or 1 volt, we then can divide those two and find the Thevenin resistance is just the ratio of those two. We're modeling that thing as basically as a big resistor. So we did example 6, and with example 6, we did this whole, this is sort of where we left it, where we did a supernode to find the open circuit voltage, and we found it was 20 volts. And then we turned off all the independent sources, so you have the circuit here with just the dependent source in there. And then we connect this, we decided to connect a current source. One. And we found out when we connect the current source that we have a current source of 1 amp here would result in a VO of 6 volts. So the R Thevenin is going to just be 6 volts over 1 amp or 6 ohms. And you might be asking yourself, do I really have to worry about whether I use a current source or a voltage source? Well, not really. It's just, one of them may be a little bit easier to solve. With a current source, we're able to find the current, so doing nodal analysis is pretty easy. At the supernode here, we sum this current, and that current. And since we have a 1 amp source here, the current through the 2 ohm resistor is just by definition 1 amp, right? So that makes it pretty easy to solve. But for now, we're going to do that same Thevenin resistance problem with a voltage source in the terminals. So we're going to find our Thevenin using a V test equal to 1 volt. Sometimes we call it V test or VO. Labeling it VT can be confusing because T is the same T, you know, it's like Thevenin, but you know, VTH is the Thevenin voltage, VT might be your test source, but then you know you got to be really careful not to mix those up, right? So VO is good, whatever, but you can call it a test voltage as well. You're just hooking up something to it to see what it requires for voltage and current. So we're going to redraw the circuit now, and we're going to have a voltage source at the terminals. We're going to add, and we're going to oops, let's just erase that last line. And here are the terminals A and B. And we're going to hook up a voltage source. Yep. Yeah, so we turned off those sources, right? This is when you're finding the Thevenin resistance. You always have to turn off the independent sources. So actually, I should have labeled that. You know, these. Oops. You can throw this out there, right? Just to indicate that that thing is turned off. So you don't forget that that's there. It was there, but it's off now. And the point is, if we hook up a, if we call this, let's just call this VO, it equals 1 volt. And we want to find out what IO is now. Is that a big deal to use a voltage source or a current source? What's the difference, right? So, well, now we know what VO is, and now we got to find out what IO is. But again, we're going to use the supernode approach here. This node here is Vx because we have a Vx here, right? And this node here is 3Vx, but why? Why is this node here 3Vx? Who can say? Because the voltage drop across the dependent source has to be 2Vx, and the only way that's going to happen is if the positive end of that voltage source is 3Vx, and the minus one, well, since the minus one is pegged to be Vx, then the positive one has to be 3Vx, because 3Vx minus Vx is going to be 2Vx, right? So again, we can do a supernode. Isn't it nice when you can see that? It really reduces your unknowns, right? You just have that one unknown, which is really nice. If you don't know that, you're going to have like a V1 and a V2 there, extra equations, and you may actually kind of drift off into the wrong answer. But 0 minus Vx over 4 is going to be the current going into Vx from below, from that 4 ohm resistor, plus, oops, let's not do that close parentheses, plus, actually the parentheses comes later, plus 0 minus 3Vx over 6. Plus, and now what's the current going through the 2 ohm resistor now that we have a voltage source there? One minus 3Vx over 2, right? So not that hard, right? 1 minus, that's the difference of having a voltage source or a current source. So we can multiply this whole thing by 4 and get that minus Vx, minus 2Vx plus 2 minus 6Vx equals 0. So Vx equals 2/9 of a volt. So that's solving Vx, right? But why are we solving Vx? Well, what we're trying to do is we're trying to figure out what is the Thevenin resistance of that circuit, right? And this is, we're trying to show this equivalency here that we can basically replace that whole circuit with a resistor of our Thevenin. Such that when you have your voltage source, of 1 volt, that your I/O is going to be equivalent. Now going back to this circuit, our circuit here that we drew, this I/O here is going to equal what? What is I/O going to equal? Mark?
1 volt minus 3 over 2 ohms.
Yeah, it's just, again, that same typical nodal current. The current I/O is the current going through the 2 ohm resistor, so it's 1, because that's the voltage source, minus 3Vx over 2 ohms. And, well, that's 3 times 2/9, so let me get a little more room here. So that equals 3 times 2/9 over 2. And that's 2/3, so 1 minus 2/3 over 2, which is 1/3 over 2, which is 1/6. So our Thevenin, once again, is just the VO over the IO. So that's 1 over 1/6, or 6 ohms. That's the R Thevenin of that circuit. So that circuit with the independent sources turned off looks like a 6 ohm resistor. We're going to be doing a fun lab next week, making a Thevenin equivalent circuit of a circuit, and you're going to be simulating it. You're going to be building it. You're going to be turning off the independent sources and measuring the resistance. All those things that we do. Only we don't have any dependent sources, but nonetheless, it's still going to be fun. Okay, so you can use a current source at those terminals A, B, or you can use a voltage source. These test sources allow us to figure out, we're sort of probing the circuit to see what is its voltage current profile like, and from that we can figure out its Thevenin resistance. Okay, so Norton's theorem is a corollary to Thevenin's theorem, which just basically says that any 2-terminal circuit can be replaced by a current source in parallel with a resistor. And that's just taking what we learned already from source transforms, saying that if we have a voltage source in series with a resistor, that's really the same thing as a current source parallel, provided those sources are linked up properly. And it turns out that the Norton resistance is the same as the Thevenin resistance. That's very convenient. And I Norton is the same thing as V Thevenin over R Thevenin, which is the source transform. Same as the source transform relationship between those two. So if you just found the Thevenin equivalent and you did the source transform of it, you would have the Norton equivalent. It's that simple. But you can also find the Norton current by taking the short circuit current at those terminals and then using that, because that equals your I Norton. Just like the Thevenin voltage is the open circuit voltage at the terminals, the Norton current is the short circuit current at those terminals. And so R Thevenin can be written also as like, V Thevenin over I Norton, or V open circuit over I short circuit. So if you had any two terminals, and this is one thing you could sort of do in the lab pretty easily, if you could safely short out the terminals on some device, you could measure the open circuit voltage without anything across it. You could short the terminals and measure the current, and then you could figure out its resistance just by dividing those two. So so basically saying the same thing, you can replace it with a current source in parallel with a resistor, et cetera, et cetera, et cetera. So we're going to find a Norton equivalent circuit of an example here, and it's the same deal with dependent sources. This one only has independent sources, so this one's pretty straightforward. But just to kind of get into the habit, you can say that I Norton is the short circuit current. So if I Norton is the short circuit current, we can actually put a wire there and just sort of see what that short circuit current is and use that in our model. So we have a 2 amp source. In this case, we have to have the sources on. We're finding the short circuit current. And we have a 12 volt source. This is 4. Oops, we have an 8 ohm resistor. Now, when we have a short circuit, it allows us to ignore the 5 ohm resistor. Why? Yeah, when you have a resistor that's got a short in parallel with it, there's not going to be any current that's going to go through the resistor if it can go through that short, right? So it's going to go to the path of least resistance. So we have a nice mesh circuit here. Because we close that terminal, we can say there's a mesh here on the left, and this mesh is by definition 2 amps because we have a current source in the outer branch there. And then we have this other mesh current here, I1, which would also happen to be what? I1 would be the same as what? Your I Norton, yeah, it's just going, the mesh current is circulating straight in there, right? So David? Should there be a second what? Oh, 8 ohm resistor. Yes, there should. Thank you. So our mesh equation is going to be that, minus 12. It's going to do this I Norton mesh, minus 12 plus 4 times IN minus 2. Is that 2 amp source coming, mesh current coming down, plus 8 IN plus 8 IN equals 0. And apparently this will tell you that you've got IN equals 1 amp, is that right? So that'd be 16 plus 4 minus 8. 12, yep, IN equals 1 amp. Okay, what about R Norton? Well, we turn off all the sources and we find the resistance at terminals A, B. So what do you get? Why don't you try calculating that resistance? At AB. And when you look at that, you should see that you've got what's in parallel and what's in series. Yep, 848 are in series, right? You got a node here, and you're going to be going through all those three if you're going to go that way, or you're going to be going through that one if you're going to go that way, right? So those two are in parallel, those two branches, and the left branch has 3 resistors in series. So Rn is going to equal H plus 4 plus H parallel with 5, which is going to equal 20 parallel with 5, which is going to equal 4 ohms. So our Norton equivalent circuit of that circuit is a 1 amp source in parallel with a 4 ohm resistor. So 1, 2, 3, 4, 5, 6 components can be replaced with 2. Has the same effect at terminals A, B. Stephanie? Why do I make the 5 ohm resistor an open when we're finding the Norton current? Well, because when I short the terminals at A and B, okay, you have a node here and a node here, and you have a 5 ohm resistor in parallel with, what's the R here for a short circuit? What's the resistance of a short circuit? 0, right? And so the parallel resistor formula tells you that the R equivalent is going to equal 5 times 0 over 5 plus 0, which is equal to 0. That means the 5 ohm isn't really thing. It's not really doing anything. Right? You can put anything you want there, but it's in parallel with a short, so it has no effect. Yeah. Other questions? How about why is this useful? This is usually about the time I get those kind of questions. Why would we bother doing this? Well, there's a lot of circumstances where it's really helpful to simplify a circuit, and I can't really tell you all those things, all those wonderful times it's going to help you in the future. But one thing we do show you in this chapter is how you can actually figure out what's the load resistor that will receive the maximum power from a circuit. Now, this actually has applications to designing power systems, whether it's AC power or DC power. If you have a generating system and a transmission line and stuff, and you want to get the most power to a load, it's in your advantage to match the load to the transmission line so that you get the most power. This is sort of how you do that. And when you have the Thevenin equivalent, you can figure out what's the most power you could get to the load and what load resistor will actually give that power to you. So that can be really useful in a power engineering kind of standpoint. Well, how do we know what that is? Well, there's a relatively short derivation which involves calculus, so we'll kind of go quickly through it. And if you can't keep up, it's not the end of the world. You can just write down the final formula, and that will be sufficient for most of what you never need to derive this, but it's kind of interesting. So the current going through the load, when you have it in a Thevenin form, is just going to be the Thevenin voltage divided by the R Thevenin plus RL. Right? That's one of the advantages of calculating the Thevenin equivalent, is that you can find the current through any load resistance that you want to put on those terminals AB that you want. So if you have a choice to choose RL to whatever you want to get the most power to the load, you can start this analysis by just using an RL there, knowing you can change that. And then the load power is going to be, for simplicity, it's going to be the load current squared times the load resistance, right? That's one way of calculating power. If you know the current of a resistor, I squared R. So the load power is going to equal, well, actually, yeah, it's going to equal, well, the IL, wait, what? IL is V Thevenin, right? Yep. So we're going to plug in this into that, and we're going to get that the load power is just V Thevenin squared times RL over R Thevenin plus RL squared. That's just plugging in IL equals V Thevenin over R Thevenin plus RL, and then squaring it, and then multiplying it times RL. So there's 3 variables to the right of that equation, that equal sign, and 2 of them are fixed, right? V Thevenin and R Thevenin are constant, but we can change RL. And so we might want to know what value of RL sets the power, which you can think of the power now as a function of RL, to its maximum value. This is where all that calculus stuff can come in handy, that you know, right? Because you want to find the maximum, what are you going to do? Take the derivative and set it equal to 0, right? And you can kind of convince yourself in the extreme case, just as a thought experiment, what would the power be when RL equals 0? Just looking at that circuit right now, what would the power be to the load if RL was a short circuit? It would be 0, right? Because the formula kind of breaks down to 0. What if it was an open circuit? What would be the power to the load? If it's open circuit, what's IL? 0. So again, your power is going to be 0 as well, right? So whether it's a short or an open, you're going to get no power. And then somewhere in between a short and open of some resistor value, that's between a 0 ohm resistor and an infinite ohm resistor. Somewhere in between those, you're going to have a maximum value. And that's what we're going to use calculus to find out, because we're going to find that dPL, the power to the load, with respect to the load resistance, we want to set that equal to 0. And that equals V Thevenin squared times, well, you've got the derivative of a quotient, right? So it's U squared minus, what is it, U squared? It's U over V, right? So it's V squared du or something, right? So it's, you guys can probably do this in your sleep, right? It's R Thevenin plus RL squared times 1, which is the derivative of the numerator, RL, minus RL times the derivative of the denominator, which is going to be 2 times R Thevenin plus RL. Over the square of the denominator, which is now going to be R Thevenin plus RL to the 4th. And we want to set that equal to 0. So 0 is going to equal, well, we can factor out, let's see, what can we say about this? Well, we can multiply both sides by R Thevenin plus RL to the 4th, and because that left side is 0, that just kind of goes away. And we can divide by V Thevenin squared, because, 0 there, that's not going to do anything either. So we're going to look at that inner part thing here, right? This part here, we want to see when that goes to 0. So 0 is going to equal, and you can factor out an R Thevenin plus RL, so R Thevenin plus RL times, see how we can do this, R Thevenin plus RL minus 2 RL. That's just the numerator with the R Thevenin plus RL removed. That has to equal 0. And that is going to be, we can't really make that equal to 0, but we could make this equal to 0. And that's going to equal 0 when RL equals R Thevenin. Dude? Could the left side equal 0 if RL was equal to negative R Thevenin? It could. And it could also equal 0 if R Thevenin was a negative. Remember I told you that when you have dependent sources, you can sometimes have negative resistances? And I was just looking at the homework, and problem 9 on the homework has a negative resistance, and it wants you to find the maximum power. So yeah, you set R load equal to the magnitude of the negative Thevenin resistance, only positive, and you will get the maximum power, but it looks like you can get an infinite number of power because you then have 0 in your denominator. But, yeah, the problem kind of talks about it. In fact, for the problem session we're going to do tomorrow and Friday, I just copied the entire homework set with the answers in it. So we'll be looking at those. In fact, we can start with the first one. Finish this thing up, but you could have questions still. Yeah, so there are some special cases which you can run into, but normally RL, R Thevenin are both positive. And so the way to make it equal to 0 is to set RL equal to R Thevenin. And when you do that, let's see, when you do that, I'm gonna have to, I do have an extra slide here. The maximum power is gonna be V Thevenin squared times, right, so we know, let's see, so P max equals V Thevenin squared. Oops, Thevenin squared up there, put the square up there. That's RL over R Thevenin plus RL squared. And this becomes R Thevenin. So we get 2 R Thevenin squared, so it's going to equal V Thevenin squared times R Thevenin over 4 R Thevenin squared. And so that is just going to equal V Thevenin squared over 4 R Thevenin. That is the maximum power that you can get. So that's an interesting thing to do with a circuit, and it uses your Thevenin equivalent, right? So now we're doing some really complicated circuit analysis to be able to determine, what's the maximum power we can ever get out of this circuit at these two terminals. And, in order to do that, you got to go this roundabout fashion. You got to do these Thevenin equivalents. You got to, if it's dependent sources, you got to turn them off, or, now you got to leave the independent, you got to turn off the independent sources, leave the dependent sources on. You got to do nodal and mesh analysis maybe to find the open circuit voltage, short circuit current, all that stuff, or hook up a test source. You see how complicated this is? This is actually a much more higher level problem. You got to do all these high level things, switch in these tools to get to this answer, which now is going to require maybe a couple pages of work to find. That's why this is the kind of the high point in the class. Once we pass this, we go back to sort of relatively simple circuits again. But we will come back to this once we go to AC circuits. Any questions before we maybe take a look at these problems? If we could go on 9 problems. We're probably not going to have time to do all of them. So we can just turn this in. Yeah, if you want to do all your homework on there and turn that in, that's fine. So as I was explaining, the in-class problems is really just the entire homework set. And there will be a quiz on this. I think I moved the quiz up to this Sunday, but I'm going to put it to next Sunday. So, because we're going to do a Thevenin equivalent lab on Tuesday, so you'll get another chance to kind of work with this stuff. And then there's going to be a pretty big quiz. You can already start doing the practice problems if you want. But the quiz I'm going to move to next Sunday. These are the in-class problems. I'm going to download this.
That quiz have
it has a bunch of problems, and it doesn't tell you necessarily what technique to use, although there are some that ask you for what's the Thevenin resistance of this circuit, what's the Thevenin voltage of this circuit. But it doesn't tell you to use superposition here or do this, because it just has an answer that you have to get. So yeah, I should really put some notes on there, like you should use superposition to try this one. This one's really easy if you use this technique. You know, this is a really good one for source transform. But you're learning all these techniques, and now hopefully you're not going to just forget them and just use nodal analysis for the rest of the class, right? You have to use the appropriate technique for the circuit. I mean, you don't have to, but you're going to do much better if you do. This first circuit is pretty, the first problem is fairly easy. You have to find R Thevenin and V Thevenin at the terminals of each of the circuits. You just have independent sources. That means you can turn off to find R Thevenin. The independent sources find the equivalent resistance. So I'll just walk around in case anyone has any questions. You can kind of check with your neighbor if you have one.